Welcome to a chemical kinetics screencast that will go over using experimental data and graphing that data to determine rate laws. In this screencast, we will be looking at simple reactions where we have one reactant, let's call it A in general, makes products, and we're going to look at the rate laws for these kinds of reactions both graphically and mathematically. And first a note, it might seem like this is awfully simplistic, A makes products, but there are in fact a number of reactions that are this simple. For example, dinitrogen tetroxide can decompose into two nitrogen dioxide molecules, so that's one reactant making products. Or the molecule cyclopropane, C3H8, can rearrange to propene, and that process also is a substance making a product, just one reactant. And there's plenty of other examples as well. Now, if we have one reactant, A, makes products, in our constrained Chem 1b universe, we can either have a zeroth order, or a first order, or a second order reaction, and the rate laws are as shown. Rate equals k times a to the zeroth power, or rate equals k times a to the first power, or rate equals k times a to the second power. Now, if it is a reaction that is zeroth order, then it can be shown that the rate equals k times a to the zeroth power can be rearranged into the concentration of A at some time t is equal to negative k, the rate constant, times the time that has elapsed, plus the initial concentration of A, which we call A sub 0 or A naught, where here the 0 stands for time equals 0. Now, this is an equation in the form of y equals mx plus b, if our y is the concentration of A at time t, and our x is time, and then the slope m is negative k, and our y-intercept is the initial concentration of A at time 0. And so if we make a graph of data for concentration of A as it changes with respect to time, notice the concentration of A just decreases linearly. So we have a straight line with a negative slope starting at the initial concentration of A0, and the slope of that line will be the negative of the rate constant. What this means is if we were to have collected data for a reaction and we knew as a function of time some concentration values, then if we graphed the data, concentration versus time data, and got a straight line, then we would know that this reaction would be zeroth order, because a zeroth order process, zeroth order reaction, gives us a straight line relationship between concentration and time. Now, if the reaction is first order, then we have rate equals k times a to the first. This requires calculus to show the next step, so I'll just give the result. But it turns out that if we have a first order rate law, then the concentration of A at some time is equal to the initial concentration of A times e to the minus kt, where again k is the rate constant and t is the amount of time that has elapsed. This can be written in a different form if we take the natural log of both sides and do a little rearranging. It can be shown that this equation is the same as natural log of A at time t equals negative rate constant k times the time plus the natural log of the initial concentration of A. And once again, this is a linear equation. It's the form y equals mx plus b if our y is the natural log of the concentration of A and our time is our x is our time, and then the slope will be negative k. So if we have data for a reaction and it's first order and we graph it, if we graph time versus log of concentration, we'll get a straight line with a slope of negative k. Now, of course, what this also means is if we have data for a reaction, we don't know its order, and we graph time versus log of concentration of the reactant and do get a straight line, then we can conclude that the reaction is a first order process, and we can determine the rate constant because that value is going to equal the negative of the slope. And if the reaction is second order, pretty much the same idea as before. The rate law is rate equals k times a to the second. Again, calculus is needed to show the following, but it turns out that 1 over the concentration of a at time t equals the rate constant k times the time plus 1 over the initial concentration of a. And once again, this equation is in the form of a linear relationship. If our x is time, our y is 1 over concentration, and the slope will then be the rate constant k. So if we have a second order reaction and graph time versus 1 over concentration of a data, we'll get a straight line with slope of k. And of course, conversely, if we have a reaction, we don't know its rate law, we don't know what order it is, but we graph time versus concentration, 1 over concentration of a data, and get a straight line with a positive slope, then we know that that process will be a second order reaction or a second order process, and the slope of that line will give us the value of the rate constant. Now, what you're going to need to be able to do is sort of go through this process, and here's a summary. If we graph concentration of A versus time and we get a straight line, that means that we have a 0th order reaction, and the value of K is the negative value of the slope. If that's not linear, then we can try graphing the natural log of A versus time, and if that one turns out to be linear, we have a first order reaction, and the slope of that straight line will equal the negative of the K value. And then if that's not linear, we have one more thing we can try. That's graphing 1 over concentration versus time, and if that one turns out to be linear, then we have a second order process, and the rate constant K is equal to the slope of that line. Now again, in Chem 1B, our choices are going to be limited to 0th order, first order, or second order, at least for simple kinetics type processes. In the real world, it's not quite this simple, but if you're doing a kinetics problem in Chem 1B, then with graphical data, or with data that we can graph, you will get one of these 3 to be a straight line. Now, you should also make sure you know how to do this with your calculator. This is just showing how to do it with a Texas Instruments 85 or 86. If you have a different calculator, you're going to have to find the appropriate buttons on your calculator and make sure you know how to do it. Your instructor is willing to help as much as he can. If you're in the online discussion, you should make sure that you come in if you have any questions or get help in the Math Learning Center, but make sure you know how to do all of this on your calculator. So on an 85 or an 86, you go to the Stat menu. You'll pick Edit, where you're going to be entering some data points. In the 85 and 86, it's the XStat and YStat lists you want. In an 83 or 84, or the calculators most of you probably have now, it's probably going to be lists L1 and L2. You'll enter your data, and typically list L1, or the one to the left, will be your X data, and the one to the right, L2, will be your Y data. And make sure, I would strongly suggest making a graph and seeing what it looks like, because sometimes you can look at it and you can see it's visibly curved, and there's no point in getting a linear regression line. So make sure you know how to get the range or window appropriate to see what the graph looks like, and then plot your points. And in this case, our sample data looks like it certainly could be linear. So in that case, what we will do is we'll calculate a linear regression line. So we'll go to Calculate, Linear Regression, LINR. On some calculators, it'll automatically do a regression line of the data that you entered. On some, you'll have to select to take a linear regression of, let's say, XStat, YStat, or list L1 and L2. And then what will happen is you will get an equation with a slope and an intercept and a correlation, and you should make sure that you know with your calculator whether A or B represents the slope. And then on this particular case, it's B that's the slope. So here the slope would be about 275, and the correlation is 0.995. The higher the correlation, the closer the correlation is to 1 or -1, the straighter your line. A correlation of +1 or very close to +1 indicates a positively sloping line, and a correlation of very close to -1 indicates a negative sloping line. Your calculator might have R and R squared instead of correlation, and same basic idea for those as well. So you should make sure that you know how to use your calculator to input and graph data from kinetics experiments, to make best fit lines and determine which one is most linear, and then to interpret your graphical results to determine the orders from the type of graph and the rate constant values from the slope, which will ultimately give you the rate law. So this, you will get multiple opportunities to practice this in class and homework, but make sure you know how to use your calculator to do this. And that is it for the Graphing to Determine Rate Law screencast.